Welcome to this week's Crunch seminar. Like every other week, this week also we have come back with two talks. Our first talk is from Professor Wang. He is a full professor in the College of Mathematics and Statistics at the Huan Normal University in China. He got his PhD degree in applied mathematics from the same university in 2011. After that, he worked as a research fellow in National University of Singapore from 2011 to 2013, and then in Nanyang Technical University of Singapore from 2014 to 2016. He became an assistant professor at the Huan Normal University in September 2013. And from 2018 to 2020, he has worked with Professor Wei Kai in SMU as a research fellow. His main research interests include fast multipole method in layered media and its applications in computational electromagnetics, higher order methods in wave scattering, machine learning algorithms for PDEs, and DG methods for PDEs. With that, please join me in welcoming Professor Wang. Thank you. You may want to.
Thank you for the invitation. Good afternoon, everyone. I'm very happy to share our research work with Professor Kanedak's group. Professor Kai and Professor Kanedaks are very good friends. And I also have many good friends in Professor Kanedak's group, like Pang Guofei, Huan Chan, and Wang Zichen. Maybe some of them are in the audience today. I have heard that Professor Kanedaks likes to work with young researchers from China very much. So in his group, there are always many young researchers from China. So as a young guy, I do really appreciate Professor Kanedaks for his help to many young people. Today, I'm going to give a report of our recent work on the convergence analysis of the multiscale neural network algorithm. We have some preliminary results on the function regression and one-dimensional boundary value problems. This is a joint work with Professor Kai and my PhD student Yuan Han, and my collaborators Wenzhong Zhang and also Liu Lizhou. My talk will have 4 parts. First, I'm going to make a brief introduction of the background and the motivation. Then I will present some results on the convergence analysis for function regression. The key idea will be extended to solving a boundary value. We are extended to the analysis for solving boundary value problems. Here we only consider a one-dimensional problem. At the end, I will give some conclusion and discuss some our future work. So here is a brief history of the deep learning. Although the research on neural network starts on 1940s, but for me, AlphaGo is the first application which makes me believe in the power of the deep learning. Recently, the ChatGPT makes another shock to the whole world. So the first work of using neural network to solve a differential equation is in the 1990s, but until a serious work of Professor Kanedak's group, the deep learning algorithms become popular in the scientific computing community. I think Professor Kanedak's group is the biggest one which are focused on the deep learning algorithm for scientific computing problems. Deep learning has achieved great success in computer vision, protein structure prediction, and natural language processing, and etc. Recent progress on deep learning for solving PDEs can be identified into 3 categories. The first category is the machine learning algorithm with physical informed neural network. Professor Kanedak's group has many pioneer work in this research field. The algorithm has been applied to various forward and inverse problems. Its simplicity and effectiveness makes it very popular in engineering. The second category is the deep reads or deep galactic method based on the variation form of the PDEs. These methods are more complicated than PIM but will make the error analysis easy. The third category is aimed for solving high-dimensional PDE. The relation between PDEs and the stochastic process are used to formulate backward stochastic differential equation for linear PDEs and forward backward stochastic differential equations, stochastic differential systems for nonlinear PDEs. Then the deep learning algorithm is developed based on the past sample according to these stochastic differential equations. As far as I know, they can solve PDEs in a domain of 500 dimensions. Compared with the great success of the deep learning algorithms, their theoretical analysis still have a lot of work to do. As in the analysis of any numerical algorithm, the most two important problems are the convergence and the error estimate. The neural technical kernel introduced by Jaggard has become a very useful tool for the convergence analysis. Wei Nanyi and Ziqing Xu has proposed a continuum formulation to describe the gradient descent training. Our work can be seen as the development of Ziqing Xu's work. We both trying to investigate the training process in the frequency domain. For error estimate, we have a universal approximation theory, and also its development, which make clear how the error estimate depends on the size of the neural network. And recently, there are also many works on the error estimate for the machine learning PDE solver. But how the error depends on the architecture of the neural network and the training algorithm is still open. Okay, let's come to our problem. We considered approximation by deep neural network. I think everybody in the audience are very familiar to the neural network and the gradient descent training. So I just want to mention in our problem, we always use this sign function as our activation function. It is essential for us to obtain some nice formulas. We will focus on the analysis for the multiscale neural network. The idea of multiscale neural network is inspired by the F principle and the multiscale wavelets. The idea is quite simple. The multiscale neural network consists of several fully connected sub-neural network, right? And each sub-network will be giving scaled input like this one, 2 product x, and the s to the power of 2 product x. And the output is just a linear combination of the output of all sub-networks. These 2 figures show us the structure of a multiscale deep neural network. We use the multiscale deep neural network to solve PDEs. These are 3 papers working on these multiscale neural networks. In our previous work, we find that the multiscale neural network generally had better performance. For example, we consider this regression problem, and the fully connected DNN and the multiscale DNN are said to have the same number of neurons. And we can see the loss function, the loss for the fully connected DNN does not reduce in the first 200 epochs, training epochs. But the loss for the multiscale DNN decrease rapidly in the first 200 training epochs. Also, this error comparison between the fully connected DNN and the multiscale DNN shows that the multiscale DNN already got this approximate function, but the fully connected DNN does not learn anything. This error is just the function fx. We also give an example for the simulation of a Stokes flow. The loss function is given by this form, and the loss is obtained from a first order system. So here we only have first order derivatives in the loss. And the multiscale neural network and the fully connected neural network are said to have the same number of neurons. In this case, the multiscale neural network has much fewer connections, and that is much fewer parameters. But the performance, the results show that the multiscale neural network has much better performance. Here, this yellow line here, the loss decays much faster than the fully connected DNN. And also the error shows that the multiscale DNN get much better results. So our question is, why the multiscale neural network had better performance? Let's first focus on this function regression problem. Here we consider a multidimensional problem, and the mean square loss is adopted. In practical training, we will use a discretization based on some sample, based on sample points. The continuum limit of the gradient descent training leads to a dynamic equation for the parameter. But after introducing the Newtonian kernel, we can obtain a dynamic equation in the function space. So for this neural network function, we got a dynamic equation. Here, this red part is the Newtonian kernel. It's Newtonian kernel. In our work, we currently only consider the 2 layers multiscale neural network. These 2 figures show the structure of this 2 layers multiscale neural network. We fixed the number. Each subnetworks have the same number of neurons in the hidden layer. So this is this number Q. This M is the total number of the neurons in the hidden layer. This M. And we take the square root of M here. That is for the use of the law of large number in the infinite widest limit. We have this p to the power of 2 as a scale in this subnetworks. In our theoretical analysis, for this simple neural network, with directly calculation, we can get this Newtonian kernel in this form. So the product leads to this 1 over m. In order to get analytical formulas, we set activation function to be sin x, and assume all the and initialize all the parameters, use independent normal distribution. We let the width of each subnetworks goes to infinity, and using the law of large number, we can calculate the limit of the Newtonian kernel in this form. We have 2 nice things in this formula. The first one is we have these separating Gaussian functions. And also each Gaussian function only depends on this x plus x prime and x minus x prime. This formula is because
what is P? Q is the number of neurons. P is what?
P is the index of this of each.
That's the number of
multiscale network.
Number of networks. Yeah. Sorry.
Number of networks. Okay.
S is the number of networks. Yeah.
Yeah. So we have this next formula because we use this activation function sign. And Jack also have already proved that the neuron technical kernel will stay unchanged during the training. So we take this infinite wide limit in the dynamics for the neural network function. We add this exact solution fx. So we got a dynamic equation for the error equation. Okay, here is a dynamic for the error equation in the function space, and we have this Gaussian function replace that neuron technical kernel. Okay, this Gaussian functions. We mark this x transpose and x prime because they will play a very important role in the Fourier spectral domain. As I just mentioned before, we investigate the dynamics equation in the Fourier spectral domain. So we introduce this Fourier transform and the definition of cross correlation and convolution and some identities. The first identity is the Fourier transform of X product and the function G is equal to the Fourier transform, the gradient for the Fourier transform divides some constant. And this the Fourier transform of cross correlation equals to the product of Fourier transform at conjugate product. This convolution, Fourier transform of convolution equals to the product of Fourier transform. So, okay, and we define this zero extension of the error function. Then our dynamic equation for the error function, there is an integral term in that dynamics equation, and that integral is on the domain omega. So we introduce this zero extension, then the integral term will extend it to the whole space, and then we take a Fourier transform in this dynamic equation, both sides, and apply these identities. We got this cross correlation and convolution, and we got this diffusion equation in the Fourier spectral domain. Okay, this is the Fourier transform of the Gaussian function, and the Fourier transform of Gaussian function is also Gaussian. So this function is real. It's real. Then we can take the real part and the imaginary part on this dynamic equation, and we get these two separate diffusion equations for the real part and the imaginary part independently. The two diffusion equations. This equation is a very standard form. Diffusion equation we can see here. We got these two gradient. This two gradient comes from the we apply the this identity twice because we have an X transpose and an X transpose and an X prime. So we got two gradient. So this two gradient here. So this is a very standard diffusion equation, and these coefficients are all real and positive. They are Gaussian functions, all real and positive. So we can have this energy equality, and due to the diffusion coefficient are positive, we can have this. We can prove the error will decay to zero if the time goes to infinity. And we also plot the diffusion coefficient in these two figures. So we can see that the diffusion coefficient got larger value as the and wide support as the scale as the increasing, as the scale increasing. So this may implies a fast convergence of the multiscale neural network. Okay, in order to show how the solution decays in this diffusion equation of this diffusion equation, we employ a Hermite spectral method to discretize this diffusion equation, and we have as all the diffusion coefficient are combination of Gaussian functions. All these matrices can be calculated analytically. So this K, D, N are all calculated analytically. Okay, then we can solve this problem in very high accuracy. Here we give some examples. First, we consider the initial error is given by this step function. And we set P equals 100 and delta T equals 0.1 10 to the minus 3. And we these are results for different coefficients. The first group of coefficients A0, B0 is for the fully connected DNN, because we if S equals to 0, then the multiscale neural network reduces to the fully connected neural network. This A3, B3 means the scale is equal to 3. A6, B6 means the error equals to 6. We can see that this the left column is for the coefficients of for the real part. The right column is the coefficient for the imaginary part. But actually, these coefficients are different in very only have very small difference. So the diffusion behavior is almost the same, But we can see that as the S increase, the solution decays faster and faster. And also, if the scale equals to 0, we can see the solution only decay in a very narrow neighborhood of 0. That means a very low frequency part, the error, the very low frequency of the error can decay in this diffusion equation. That's why the fully connected DNN cannot approximate high frequency functions. And the second example, we consider a regression problem. We give this a target function, and we choose this target function because we can calculate this Fourier transform. We can calculate the zero extension of fx. The Fourier transform is given by this formula, and also we use this sin x as an activation function. So the Fourier transform of the neural network also with zero extension. We can calculate the Fourier transform. Give this analytical formula. Then we give that error, the initial error just this f hat minus this ns hat as the initial error. This parameter we just randomly initialized using a normal distribution. Fix a group of parameter, and we can see the decay of this initial error. If the scale equals to this one, the first one is scale equals to 0. The second one scale equals to 3 equals 0. That means fully connected DNN. So the error in Fourier domain decays very slow, and only a small part in the neighborhood of 0 decays. But for this scale equals to 3, you can see that this purple line. The purple line, we run, I think we run 10 to the minus 5, 10 to the positive 5 steps. So we got time equals to 100. And this purple line, you can see is the area is much smaller than the fully connected DNN. This is the imaginary part. And we also use example to verify that the diffusion system is to verify our theorem. We use the machine learning algorithm to learn NS, and we also use the initial error to the diffusion equation, and we run the diffusion equation in the Fourier domain. Then we take an inverse Fourier transform back to the physical domain and compare the results with the numerical solution obtained by the machine learning algorithm. Because this we use a Hermite function in the Fourier domain in solving this diffusion equation. This inverse Fourier transform can be calculated analytically because this Hermite function, the Fourier transform is just scaled Hermite function. So what these formulas are analytic. Then we compare the results. This is the initial error. They are the same. We set the same error. But the diffusion equation, we need to calculate the Fourier transform. And then we can calculate to t equals to 20. We need to emphasize the time steps is equal to 10 to the power of minus 3. So here we already run like 20,000 steps. This is 50,000 steps. This is 100,000 steps. So we can see the results match quite well. And we use the widest of this neural network is like it's only 2,000 for each subnetwork. So the total number of neurons in the hidden layer is 8,000. So this is much smaller than, it's not a very big number, right? But the results matches very well. Okay, then we consider, we extend the idea to the 2-point boundary value problem. We consider this a 2-point boundary value problem.
Can I ask, Bo, can I ask here? So you only consider continuous functions, right? Yes, so far you didn't, like if you have a finite discontinuity, you cannot treat it like that.
Yeah, currently we only do this test for this continuous function because we can calculate the Fourier transform analytically. Otherwise, maybe we cannot calculate the Fourier transform. But we are trying this.
We have a function that we use for our test where we have like low frequency on the right, high on the left, high frequency on the right, and then there is a discontinuity in between. So
okay. Yeah.
How we observe the spectral bias and actually, what happens if you look at how the spectral bias works there? Yes, you do resolve the left side first with a low frequency, the high frequency. Then, it starts actually the very first epochs.
Okay.
Neural network will try to capture the discontinuity. Then immediately goes back to the low frequency. Then it goes to high frequency, and then after it's done with this, finite spectrum, it goes back to the discontinuity, which has an infinite spectrum, right? A very long tail, and it does that. Mm-hmm. So I'll show you a video of that because I'll send you a video because it seems to me that deserves, there will be another term, and I don't know if you can use like a Gegenbauer decomposition David Gottlieb introduced, where you can do the discontinuity, and therefore you can treat it again instead of Hermite polynomials. You can do Gegenbauer reconstruction, then Hermite, for example.
Okay, you mean solve this diffusion equation?
Yeah, well, yeah. I mean, to first to analyze, to decompose the function two parts, the continuous and the discontinuous part.
Okay. Thank you for the comment.
Yeah.
Okay, the second part is on this two-point boundary value problem. The main idea is almost is same. So in order to take care of this boundary condition, we use this interpolation of this neural network function. So the loss function is also the mean square loss function. So this is only the second derivative of W is in this loss function. And we define this zero extension of the error, and we take this, we derive this dynamic equation for the error, and we can see here the Newtonian kernel. Here we have this second order derivative on this Newtonian kernel, but this is okay. We can handle this. So the error here is the also the second derivative of the error. And we take this infinite widest limit. We got this the limit of the Newtonian kernel, and then we calculate this second order derivative is also the derivative of Gaussian functions. Okay, so we take a Fourier transform in that error dynamic equation, and we got this dynamics equation in the Fourier domain. Here we have this cos square over 2. This is from this from the second derivative of the Gaussian function. So, and the first derivative of the Gaussian function give us this cos, and this cos square over 2 and this cos, these two terms can be combined into this one. We have this cos square inside, and take the derivative of cos here. So these two terms just combined into this nice one. Okay, so also this Fourier transform of Gaussian function are the real functions, right? So we take a real and imaginary part. We have these two separate diffusion equations, but this unknown function is the cos square product, the Fourier transform of the second derivative of eta. So this is the coefficient. The coefficient is just the one-dimensional version of our old diffusion coefficient. So, and in order to write this diffusion equation into a standard form, so we introduce this omega, which is equal to the cos square product of this Fourier transform. And then this equation is rewritten, reformulated into this form. So we have this cos, the power 4 of cos here. So this is a very strong singularity here, but at this W is defined equal to the square cos square product that this L, the Fourier transform of this L. So we only concerned the decay of this the second derivative of eta, right? Because we already take care of the boundary condition. So we only need to consider the decay of this the area of the second derivative of eta. So for this diffusion equation, we can also have this energy inequality, and this we can also prove the diffusion, the solution will decay, and as this W equals to the cosine square product, this Fourier transform, we substitute this one to this energy term, and we have it will cancel this cosine square. So we will the energy equality will implies the Fourier transform of the second derivative of eta goes to 0 as t goes to infinity. So in physical domain, we have this decay. So how to solve this diffusion equation? We have the singular term. Because this W is equal to the cosine square times the eta, the Fourier transform of a second derivative of eta. So we just add this square, cosine square in the basis. Then we use a Galecki method. We have this one have a cosine square term, and this term will have another cosine square term. So this cosine power 4 will cancel with the cosine power 4 in the denominator. Then we have this linear system. Everything is okay. And also all these metrics can be calculated analytically, because this A, the coefficient is Gaussian function, and this cosine square, we can use the recurrence formula to calculate, to derive analytical formulas for all these metrics. So we can also have some numerical results. We give this initial array, and we want to show the decay of this diffusion equation. Here the diffusion behavior is quite different with the function regression problem. You can see some of these area will increase in this low frequency domain. So we still are trying to okay, this is typo, I'm sorry. So we are trying to explain more about this this phenomenon. We're trying to do more numerical results to analyze how this will affect the convergence of the machine learning algorithms. But as the scales increasing, we can see the solution will decay faster, and even high frequency parts can decay. And we also consider this exact solution and give this initial error into this diffusion equation and solve the diffusion equation. The solution shows for fully connected two-layer neural network, only this very narrow neighborhood of the zero decays. But for the multiscale two-layer neural network with scale s equals to 3, the purple line is the time equals 0.1. For this diffusion equation, I think the resulted ODE is much steep. So we need to use much smaller time steps. So for this simulation, we use time step. Okay, let me see. Okay, actually we use the time step 10 to the power of -5. 10 to the power of -5. So for this t equals 1.0, we already run like 10,000 steps. Okay, this purple line show the error is very small. Only a very small part in this in this low frequency domain are still here. Okay, this is for the imaginary part. Okay, let's come to the conclusion. We analyzed the gradient descent training for the regression problem and show that the training in the frequency domain tends to a diffusion process. And also we consider the two-point boundary value problem. And we also got a diffusion process in the free spectral domain, but the coefficients is different because we have that cosine term. So the decaying behavior is quite different. And our results show that the multiscale neural network have much faster convergence than fully connected neural network. Our ongoing work is only we are trying to consider other activation functions, and also we want to consider this multi-layer neural network. Maybe we can extend this idea to some other architectures of the neural network. Okay, thank you for your attention.
Thank you, Professor Wang. Do we have questions for, yes, Natras, you can go.
Thanks, Samdata. Bo, that was an excellent talk. I have a question. I'm not sure if it's relevant, but I was interested in you get in the kernel, you get the exponential with x plus y and x minus y.
Yeah.
And I'm curious if there's a connection with with radial basis functions and like in a x minus y kernel, you would think of as like a RBF with approximation properties. I'm curious if there's a connection there in the x plus y. I don't know how to think of that as a kernel. So I'm curious if you have any intuition, or maybe there is no connection to radial basis, like maybe there is no approximation properties there. I'm just curious if you think that's a meaningful way to interpret the kernel.
Actually, that x plus x prime and x minus x prime is very important in my derivation, right? Because this gives our cross correlation and convolution. So we can use these identities in the derivation. Then we get a very nice formula. I think this x plus x prime and x minus x prime comes from that activation function sine, cosine. Because sine, cosine, we can have the we can have an identity for the product of two sine function. We got the plus form, right? So that's why we have this x plus x prime and x minus x prime.
Yeah, exactly. I mean, my question is more, it goes to how you would design the activation function, right? So if you want to design the activation function so that the Fourier transform has certain properties, right? I can follow how for your specific choice, it fell through the analysis. Right? But in general, like, I'm trying to understand what design principles, if you want to try different activation functions or different, but anyway, thank you. It's an excellent talk.
Okay, thank you for the comments. I think we will try. Your suggestion is very valuable, I think. Yeah, we can try this activation function maybe.
Yeah, this is Thomas. Speaking of the activation function, will GELU be okay?
Sorry?
Will GELU, GELU activation function work in this case?
I don't think so.
Yeah, it's called Gaussian error linear units. Will that work in this case?
I think my derivation is very strongly dependent on this activation function. So
okay.
If you want to get this nice formula, you have to use this sine function. If Maybe other functions we can get some nice, some other nice formulas, but I'm not sure. Thank you.
Okay. Okay. Thank you.
Hi, this is Kamal from Transgo. I have a small query on slide 7.
Sorry, say it again.
I have a small query on slide number 7.
Slide number 7.
Yeah. This input to the multiscale DNN is a geometric series. Can we use different series?
Yeah, of course. Yeah.
But any recommendation, like, is depend upon the any output function, anything? How to choose the input function?
According to our experience, I think this power of 2. Currently, we found it is the best one.
Okay, thank you.
Thank you.
Maybe can I ask you a quick? Yes, thank you.
Yes, correct, please.
Thanks for a very nice talk. I have a quick question about the initialization. So in this framework, you explicitly put the 2 and the 2 to the power in your input, but equivalently, we can think of like we initialize the weight according to changing the variance of theta, because that's simply we can multiply 2 to the p like in the variance, then I think that's a lot. And then I think the analysis still goes through. Then does it tell us, do you see any discrepancy between putting 2 to the power explicitly or changing the initialization of the theta? Because the statistical property should be the same so that you will still get the same Gaussian kernel. And you still get the, I don't really see any big loophole through the analysis. So that I just got curious whether do you expect any discrepancy? If not, I think it might be interesting to see whether there is any performance difference between putting explicitly 2 to the power as an input versus changing the initialization.
You mean the initialization of the parameters of the neural network?
Yeah, sure. Because if you see, I think the next slide where you see the explicit formula of your network, then you see that theta is theta times 2 to the px appears. Then we can also think about the other way around that, all right, then say 2 to the p is multiplied by theta, then which is corresponding to changing our Gaussian normal distribution with the variance 2 to the, actually 2 to the p is squared.
In that form, if you use your framework, I think this subnode works will have many overlap, right? Because you give this one the variance of like 2, then you get this one 4, then this 4 will cover that 2, right? The parameters will cover that 2.
So I think can you move to the slide where you see explicit formula of your network?
Okay, this one.
Yeah, here. So what I'm trying to say, let me see if I can annotate. So currently you see this as an input, this is a network parameter. But what I'm trying to say is, actually you can see this as your parameter, and this is your input. So that what I'm trying to say is, all right, and if this is the case, theta is coming from the Gaussian normal, you can think of this is the Gaussian normal from 0, variance 2 to the p's power, which is 4 to the 4. Then all you need is just changing the variance of how you initialize your network.
Okay, yeah.
Then I don't really see from the analysis whether it would highly impact it or alter your result. I think you still get the same result because eventually you let the width goes to infinity, then it comes down to the expectation. Then from the statistical property, these are the same.
Yeah. I think you're right. I will try this. Thank you for.
I think it might be interesting to see whether you see any discrepancy in the performance. I mean.
Yes. Thank you so much. Yeah.
Yeah, great talk. Thank you.
Thank you. Very nice. Thank you.
Thank you, Yonjin. There are more questions for Professor Wang.
Why did you try to also compute the convergence rate? Because at least for the examples that you have, you can take the error and then you see with respect to S. My biggest question was actually that. Even for these specific examples that you have,
we want to show our analysis is correct. We just want to verify our analysis.
I know that. Actually, one of my postdocs, ex-son, had derived this type of residuals for integration by parts and different methods, and show the residuals. So one layer is not difficult to derive this. It's just a matter of, but at the end, what we really want to see is that how do you choose S, right? I mean, that's the theory would guide us to say how many networks we need, and therefore I need to know for a certain band of frequency, a bandwidth, I need to know what is the value of S. So in order to do that, to choose a priori, I need to know what's the convergence rate with respect to S. So I think that you can actually fit some of your results, and even from the analysis, you can find out what is the convergence rate.
Okay, thank you. Thank you for the comments. Yeah, thank you. We'll try. Thanks.
So thank you, Professor Wang, taking your time and being awake so late.
Okay, thank you, Sondata. Thank you all for the comments. Yeah, it's very helpful. Thank you very much.
Thank you. So we move on to our second speaker. Our second speaker is Paula Chen. She is a fifth-year PhD student in the Division of Applied Mathematics at Brown University. Her research areas include Hamiltonian-Jacobi partial differential equations, application in optimal control and efficient algorithms for evaluating Hamiltonian-Jacobi PDEs in high dimension. And she would be talking to us about lost landscape engineering via data regulation on PIDs. With that, please join me in welcoming Paula.
Yeah. All right. Can you see my slides?
Yes.
Okay. Thank you for the introduction, and thank you, Professor Kornodakis, for inviting me to speak today. So just to be clear, this presentation is not on my own research, and instead I'll be presenting this paper, Lost Landscape Engineering via Data Regulation on PINs by Gopakumar et al. And this paper, the preprint is available here. Okay. So just for a brief introduction, consider the following nonlinear PDE. So here, gamma represents the time derivatives, lambda is the space derivatives, f is the initial condition, and g is the boundary condition for this nonlinear PDE. As I'm sure we all know, the PIN approach has been very popular and has numerous advantages over the traditional numerical methods for solving nonlinear PDEs, such as this one above. And the PIN loss essentially solves this PDE using this PIN loss here, which we define as the sum of these three loss functions. The first one being enforcing whether or not the neural network solution satisfies the PDE. The second one enforces that the solution satisfies the initial condition, and the final one enforces that the solution satisfies the boundary condition. And here I'm following the notation of the paper, so I believe that they're missing some norms here to make this a more legitimate loss function. Okay. So for the motivation of this paper, generally when we speak about neural networks, there are three main sources of error in neural network solutions. The first one is the approximation error, which is related to the universal approximation theorem for neural networks. So how well does the neural network solution actually approximate the function that we want to approximate? The second source of error is generalization error, which is related to the training set used to train the neural network. So essentially, how well does the parameters that the neural network learned in training generalize to new test sets? And finally, the last source of error is optimization error, which is related to how well does the optimizer achieve the minimum of the loss function. So the main goal of this paper is to explore how adding different types of regulating training data, which I'll define more specifically later, affects the topology of the pin loss. And here, I think we're using the topology or term topology a little bit more informally than what would be most mathematically rigorous. So the main goals in doing this would be to decrease approximation error by improving convergence to the unique solution to the PDE, which we know would be unique if the PDE is well defined. And this should correspond to a unique point in the loss landscape. Another goal of adding this regulating data would be to decrease the optimization error by accentuating the minimum of the loss function and or otherwise altering the topology of the loss landscape. Of course, all of these things are complicated by the fact that this loss landscape is generally non-convex and we have these competing multi-objective losses. So from the previous slide, that corresponds to that domain loss, the boundary loss, and initial condition loss. And then in this paper—
Can I ask you a quick question?
Yes.
When you say topology, do you mean like topography or do you mean like the connectivity of the loss landscape?
Yeah,
like, is this just like how rough it looks and stuff like that?
Yeah, I think it's the latter. So it's more like the topography of the loss landscape, but I use the word topology here because it's the term that the paper uses. But generally it's very qualitative observations about what the loss landscape looks like.
Great, thank you. That's helpful.
Okay, and so in this paper, we also ignore generalization error because if we add regulating data, we generally, it's well understood that this would increase generalization error. Okay, so for an outline of this talk as well as the paper, we're going to do a brief overview of the method for visualizing the loss landscape used in this paper. Then we're going to discuss what the general pin setup is for this paper, and then we'll discuss 3 different methods of adding regulating data to the pins. The first method is sparse regulated pins. The second is coarse regulated pins. And the third method is using experimental data as the regulating data. And then for the first method, we'll go through 3 examples: the 1D Burgers equation, the 2D wave equation, and then the 2D Navier-Stokes equation. And then we'll revisit this third example for the other 2 methods. And then finally, I'll have some summary of what the paper found, as well as discussing 2 more related works that also look into loss landscapes of neural networks. All right, so for visualizing the loss landscape, obviously the loss landscape is some very high dimensional thing, since we essentially have as many dimensions as the number of parameters in the pin. So to visualize a loss landscape, we pick 2 orthogonal directions in the parameter space to project this loss landscape onto. The paper is not so specific about how exactly they picked these 2 orthogonal directions, but they cite this paper by Li et al. Called Visualizing a Loss Landscape of Neural Nets. And so I believe that this is what they mean by these 2 orthogonal directions. So the details are not super important, but I'll just highlight some main qualities of why you might want to pick these particular directions. So one quality about these directions is that they are what is known as filter-wise normalized. And what Li et al. Found is that this correlated, or using these directions, had a stronger correlation between the sharpness of the loss landscape, so how sharp it is near the minimizer, and the generalization error. So generally, if there was a sharper minimizer, then you would have larger generalization error and vice versa. And then the second characteristic about these directions is that we wanted these orthogonal directions, which were picked as the first 2 principal components of this matrix M here. And here, theta sub I represents the neural network model parameters after the training epoch I. And the intuition behind using these particular directions is that you want to capture as much variation in the trajectory of the optimizer as possible. So if you were to use some random directions that were not these 2, then there's some chance that you might miss some characteristics of the loss landscape. All right, so here we have the general pin setup. So these regulated pins, which are the main focus of this paper, are generally identical to the vanilla pins, except we add in this reconstruction loss into the pin loss. Again, I think there should be norms everywhere here. So this is a legitimate loss function, but we can ignore that for now. So here in this final term, we see that U tilde is the neural network solution to the PDE, and U is the exact solution at some points XS, which we will define for each method later on. And here this differs from the previous two terms because this term is constrained to be for the initial condition. This one's the boundary condition. So these XS's could be at any time or any space in the domain. Okay, and then here, I believe these are just some pretty standard characteristics of pins that they used here, but I've included them here in case you're curious. And notably, they use quasi-Monte Carlo to do integration. Okay, so for the first method, we discussed sparse regulated pins. And what this means is that these points that they chose in this reconstruction loss come from some sparse simulation data points. So these sparse points are just some randomly sampled points across the domain. We know in practice already that using this kind of data in the loss function should decrease both the approximation and optimization error. And then we would like to just look at what that does to the loss landscape and if we can see any correspondences to why this might be the case, I guess. And we also assume that the sparse data is accurate, so we're not accounting for noisy observations or anything like that. Right. So for the first example, we do 1D Burger's equation. Again, this is the notation in the paper. I believe that they actually mean to write the viscous Burger's equation here. So this should probably be equality, and this should be a second spatial derivative. Regardless, the exact solution is computed here using some spectral solver. They're not too specific about which kind, but I don't think it's super important. And then here we're going to train the sparse regulated pin with 1% sparse data. Okay. And so here is an overview of the results for this example. We'll take a closer look at the bottom figure in the next slide. But in the top figure, we can at least see that the vanilla pin, which is a little bit hard to see, but the results are in green. And then the sparse pin is in blue and the exact or numerical solution is in red. And we see that adding the sparse regulated data does help the pin to converge to the correct solution. And the errors are in fact smaller when we use this sparse regulated data. Okay, so now taking a closer look at the loss landscape. So on the left, we see that when we don't add any regulated data, we have a relatively bumpy loss landscape with a not so clear minimizer. And here on the right, we see that when we add 1% sparse data, we accentuate where the minimizer is. And the authors then say that this should help the optimizer to converge. So the next example is the 2D wave equation. Again, we use some sort of spectral solver to compute the exact solution, and we train the pin with 1% sparse data. Okay, so here's an overview of what the results were for this example. Again, we'll take a closer look at the loss landscapes on the next slide, but just to look on the figure on the left, we see that the top is the exact solution. The middle is the vanilla pin, and then the bottom is the sparse regulated pin. And we see that the addition of the sparse regulated pin decreases the error a little bit and makes it converge a little bit more closely to the numerical solution. Okay. All right, so zooming in on these loss landscapes, again, we see that when there is no sparse data, we do kind of see a clear minimum, but the loss landscape in general is relatively bumpy. And then when we add in the sparse regulated data, the minimum becomes a little bit clearer. And again, the authors claim that this makes the loss landscape easier to traverse, and so that the minimizer is easier to reach.
Oh, sorry, this is Lulu. So I have one question here. Can you go back to the first example, the loss landscape in the first example?
Yes.
So it seems to me in these two plots, the left one, no sparse data, the loss landscape looks better than the second one.
Yeah, I was going to get to that in a later slide where they like do a comparison of adding different levels of sparse data. But yeah, to me, in terms of optimization, like if I were to look at this loss landscape on the right, if you were to use like a first order or gradient-based optimizer, which, you know, the Atom optimizer is one example of those, I'm not so sure that this loss landscape is really preferred over the first one, because as you can see, like, yes, there is a clear minimum, but as you approach the minimum, the gradient is kind of exploding, which is not really favorable behavior for those types of methods. But again, this is what the authors claim, that, you know, you see this more distinct minimum. They say that it should be easier to traverse and easier to get this minimum with the optimizer.
Yeah, that's it. Yeah. Also, in your previous slide, you mentioned it. Usually people claim larger slope means larger error, right?
Yeah. So the paper by Lee, that using
the sharpness,
they said that, yeah, this sharpness would lead to a higher generalization error. But I guess that should be offset a little bit by possibly the optimization error being lower and the approximation error being lower.
Okay.
Paula, do they have the histories of the loss in the two cases? Because we can see from there.
I'm sorry, could you repeat that?
The history plots of the loss, of the respective loss on the left and the right. So loss versus epochs.
I don't think I have a picture of that.
You know, if they had in the paper, that would be informative.
Yeah, I don't think they include one of that, because I'm basically including every single figure that this paper has. But yeah, I don't think they plot the actual trajectory, but you can imagine that the trajectory of the optimizer is somewhere along this figure. Do we have any more questions?
Please proceed.
Okay. All right, so the last example for this method is the 2D Navier-Stokes method. Again, I think there's a few typos here, like this should be a second derivative in y, and it's hard to tell if these are actually the same symbol or not, but some of these are v's and some of them are news. Also, the authors say that here for Navier-Stokes, what they're actually simulating here is fluid flow around a rectangular block. So these definitions of the domain is a little bit imprecise, because they just say, just use the appropriate boundary conditions to enforce this rectangular block. And then again, we used some traditional numerical solvers to compute the exact solution. And then this time we're going to test the sparse regulated pin with either 1, 5, or 10% sparse data. Okay, so here's an overview of the results for this example. I'll look more closely at the loss landscapes on the right in the next slide, but for now, let's just focus on the left figure. So on the top, we have the exact numerical solution. The middle, we have the vanilla pin, and the bottom is the sparse regulated pin. I believe this should be the 1% sparse data, but don't exactly remember. But we can see either way that the addition of the sparse regulated data does decrease the L2 error, and we converge a lot more closely to the exact solution. Okay. So now looking at the loss landscape, we see that when we have no sparse data, we have this relatively bumpy landscape, and again, no clear minimizer. But as we add sparse data, the minimizer becomes more pronounced, although not sure how clear it is, but you can see that there are like a lot of bumps as we head towards the minimizer. So I think in this 1% sparse data, the authors even say that they get stuck in a local minimizer or local minimum here but that if you were to like add a little bit of noise, you should be able to converge to the correct minimum. And then they also claim that this more accentuated minimum provides better convergence for the optimizer. But as we discussed earlier, I'm not so sure if that's actually the case.
Hi, this is Suko here. I had a question on the sparse data. Do they use the exact solution to compute the sparse data?
Yes.
They don't use an approximate solution, which is like a coarse solution to use the sparse data, because it's not fair. You don't know the exact solution typically.
Yeah, so here they're using the exact solution, or I guess exact as in a fine mesh.
Right.
But
it might be more interesting to try it with a rough solution, which is in the ballpark but not exact.
Yeah, so that will be the next method, actually.
Oh, okay.
Okay. Okay. So moving on. Okay, so method 2, we have the coarse regulated pin, which is exactly what you just asked about. So again, the loss function is the same as for the sparse regulated pin. There should be norms everywhere. But instead here, the addition of this regulating data comes from some coarse simulation data. So here the motivation is that, simulating sparse simulation data is pretty expensive. So we want to replace that with some sort of coarse simulation data. And then the authors even pose this rhetorical question, like if you had access to the exact solution using this numerical solver, why would we then use a pin? So the idea here would just be to build like a quick coarse approximation using a numerical solver and then fine tuning that solution using a pin. And then hopefully this should overall be less computationally expensive than just using the traditional solver. Okay. What?
I had one more question. Did they try, suppose you take the sparse data and you solve the problem, right? You've got some solution for the thetas, right? Then you drop the sparse data and try to train it again with the initial guess of the previous solution.
Mm-hmm.
And I'm sounding complicated, but I don't know if that's possible or not. Or
it's probably possible. I'm not sure if the computational gain of that would be that good, because as we said, the sparse simulation data is pretty expensive to simulate, just because it's randomly sampled, and so you kind of need a pretty fine-tuned grid to compute those in the first place.
Yeah, sorry, I can go ahead.
No worries. Okay. So for the first example, we again return to the 2D Navier-Stokes equation, same typos as before. And then also the fluid flow is again around a rectangular block. So here the exact solution is computed using this finite difference solver as before. And the coarse regulated pin is trained on data built from a coarse solver with a mesh 10 times coarser than that used to compute the exact solution. Oops, okay. Wait, sorry, I think I skipped a little. Okay. So we'll look at the figure on the right more closely in the next slide, but again, to just look at the overview of the solution that we get. So the top is the exact solution, the middle is vanilla pin, and then the bottom is the addition of the coarse regulated pin. And similarly to before, we see that the addition of this regulating data does in fact make us converge to the exact solution more closely than the vanilla pin. Although of course, as you can see in most of these figures, there are still some errors everywhere. Okay, so now let's look a little bit more closely at the loss landscape. So on the left, this is when no regulating data is added. The middle is when we add 1% sparse data, and then the right is when we just have this coarse regulated data. So you can see that the effect of adding this coarse regulated data is similar to adding the 1% sparse data. The minimum becomes more clearly defined, although we still get a lot of bumps on the way to the minimum. And then again, the authors claim that because the minimum is more clear in this picture, that the optimizer should achieve the minimum more easily. But same caveats as before. All right, so for the final method, we are using experimental data as the regulator. So again, the same pin loss as before. And here the exact solution comes from some experimental recordings of the exact solution. Okay. So as an example, we again return to the 2D Navier-Stokes problem. Same setup as before. Here they're simulating collecting experimental data so we have this rectangular block that the fluid is flowing around. We're going to fix one point before the block and then one point after the block. And then periodically we'll just measure what the solution is at those points. So looking at the results here, we'll look at the figure on the right a little bit more closely in the next slide. But on the left, we can see the top is the exact solution, and then the bottom is their experimental data regulated pin. And we see that there is quite a large error when we have this regulated data, and clearly the effect of adding this type of regulatory data was not as great as the previous examples. Okay. So looking at the loss landscape a little bit more closely. So this top left figure is no regulatory data. This bottom left one is 1% sparse data. This top right is when we have the coarse regulatory data. And then this bottom right is when we have the experimental data. So we can see that adding the experimental data didn't really help that much. So we still get a very bumpy landscape. The minimum is not that distinct. And so the authors just concluded that adding this type of data lacked sufficient impact on the loss landscape for convergence of the neural network. I think intuitively this kind of makes sense too, because based on how they described simulating this data, this added a lot less regulatory data than these two examples. Okay. So for a summary of this paper, the authors demonstrate how challenging loss landscapes for pins can be to traverse. They showed that adding regulating data of any kind does in fact alter the loss landscape, which in some cases can increase the performance of the optimizer. As a result, they did observe some improvements in the performance by an order of magnitude in some cases without increasing the training time for the neural network. So I am going to talk about some related works now, but does anyone have any questions so far?
So I had a question. This is Suku again. So one point that what I was thinking, I was like, I forget now. I'll come back later.
Okay. Yes. Konstantinos?
Okay, thank you. Nice work. Actually, I would like to ask you this. Most of the cases, what present about loss landscapes depends also on the optimizer that you use. I mean, it's not clear to me the influence of optimizer, how it affects your loss landscape. I mean, of course, you know, because it can be an interplay about the optimizer that you're using and the number of data that you're using and the structure of your pin.
Yeah, I think that would be interesting to explore. I know in this paper, they said they used the Atom optimizer. I can go back to the details if that's something that interests you, but
yeah, okay.
I don't think they explored.
Just a comment, because it's not, yeah. I mean, not all optimizers will work, you know, with the same amount of data, or, you know, I think there's an interplay between them. All right. I mean, it's like, you know, maybe you can investigate this as a next step.
Yeah.
Yeah, I remember my question now.
Yes.
Here. Yeah, one was, did they vary the number of training points to see how the landscape changed, or?
So they did for the sparse regulated data and the 2D Navier-Stokes problem, right? So here they added different amounts of sparse data.
No, not in the sparse data, in the data itself, in the points they chose in the collocation.
Oh, I don't think they changed that.
Okay. And the other thing is, I presume they did not study a hard loss versus soft loss boundary conditions itself. Like
no,
if they go
but the next related work that I'm going to show, they use like an augmented Lagrangian to enforce the boundary conditions. So that is probably related to your soft boundary
Okay,
conditions.
I'll come back to that then.
Okay.
Okay, sounds good. Thanks.
All right. Cool. All right, so for the first related work, we have this paper, Critical Investigation of Failure Modes and Pins by Bazier and Sanojak. So here they compare 3 different methods. The first one is a purely data-driven regression model. So this is actually not a pin. It's just using these, essentially what the main paper called regulating data. The middle is the vanilla pin pretty much. So this term is just enforcing that the solution to the neural network satisfies the PDE. And then the second term, which is equation 7, is enforcing the boundary condition. And then this paper defines what they call PCAN, which essentially just uses the augmented Lagrangian method to enforce the boundary conditions. And so this is their overall loss function here. Okay, there's a lot of information on this slide, but I will look more closely at the loss landscapes on the next slide. But just as an overview, this is an example using the 1D Poisson equation. Here in this paper, they just say that they project on 2 random directions. So as you recall from an earlier slide, we stated that if you use 2 random directions, you might miss some characteristics of the loss landscape. And we're not necessarily sure that if we see this like sharpness of the minimizer, that actually corresponds to a higher or lower generalization error, because they didn't use the filter-wise normalized directions. Right, so looking more closely at these loss landscapes. Oh, sorry, let me go back once. Where's my mouse? Okay, so here they just pick the solution to the wave equation to be the sinusoidal wave, and then they're going to vary the frequency of this wave, omega. Okay, so now looking at the loss landscapes, the top is the purely data-driven neural network. So this is not even a pin, it's just using those, what we called regulating data points. The middle is the vanilla pin, and then the bottom is PCAN, which is using the augmented Lagrangian to enforce the boundary condition. And then as we go from left to right, we're increasing how oscillatory the solution is. So we see that for the pure data-driven neural network, we maintain a pretty distinct minimum throughout, although the loss landscape does get bumpier as we increase the frequency of the sinusoid wave. We do note that this is pretty similar to the results that we saw in the main paper of this presentation, which is that we see this relatively bumpy loss landscape when it's away from the minimizer, and then as we get to the minimizer, it drops pretty drastically to it. And then for the vanilla pin, we see that we increasingly get non-convex behavior as we increase the frequency. So we interpret this as being more complex to optimize. And then for the bottom with PCAN, we see that we do maintain this distinct minimum as we increase the frequency omega, but we have a generally smoother landscape than for the vanilla pin. So the authors here interpret this as being that the PCAN loss is easier to optimize than the vanilla pin.
Do you know what mu they used for the parameter?
I don't recall, actually. Sorry.
So it might be a function of mu. It's basically known to be a function of mu.
Yeah.
So.
Yeah, I don't really remember what they picked for that though.
It's like a penalty, basically. So
yeah,
that's okay.
Okay, so I think I have. Yeah. Wait. Sorry. Okay, so for the next example, they look at the 2D Poisson's equation. We'll look at this bottom figure more closely in the next slide. But in the top, we can see what the solution recovered by each method looks like. So here we have the exact solution. This one is the regulatory or data-driven regression method. This one is the vanilla pin, and then here's PCAN. So we see that the vanilla pin did not really recover the solution, which we'll talk about in the next slide, but essentially it got caught in a local minimum and didn't actually converge. Okay, so looking at the loss landscape for this problem, we again see generally the same trends that we saw before, where the data-driven one has this clear minimum. Pecan is somewhat similar to that one, but has some more oscillations around the outside of this loss landscape. And then for the vanilla pen, it's highly non-convex, and the minimum is less distinct than for the other two methods. So here we note that, yes, the optimizer was able to find the minimizer for Pecan and also for the purely data-driven regression neural network, but for the vanilla pen, we got stuck in a local minimum and the optimizer was not able to find the true minimum. Okay, so do we have any questions before we move on to the second related work?
So here also they did not mention how with mu things changed, right?
I don't think they did.
So they just chose the optimum mu that they found essentially, right?
Probably, yes.
Yeah, okay.
Yeah. But I think their conclusion is mostly that by doing the augmented Lagrangian instead of the hard constraint on the boundary, we kind of get this smoothing effect of the loss landscape. Okay. So for the final related work, this is actually the paper by Lee that we discussed in a previous slide, which had defined those filter-wise normalized orthogonal directions. So I'm just going to highlight a couple examples on this paper. This one's not focused specifically on pins, but just neural nets in general. And they talk about a lot of different features about neural network architectures and how that may affect loss landscapes. So yes, let's go to the first example. So for this one, this figure is showing the effect of the loss landscape of using skip connections. If you don't know what skip connections are, very briefly, those are essentially a way to prevent overfitting in deep neural networks by using some sort of heuristic formula to decide whether or not you skip layers in the neural network. And I believe skip connections were originally formulated because some deep neural networks were not able to recover the identity function. So they basically formulated these skip connections so that that was possible. And in general, these are used heuristically to prevent overfitting and also to prevent the exploding or vanishing gradient problem that a lot of deep neural network experience. So we see on the left that this is a neural network with no skip connections, and on the right, we do have skip connections. I believe here, even though they did discuss the orthogonal directions later on, they're just using two random filter-wise normalized directions. So here we see that the addition of the skip connections leads to a flatter, less non-convex loss landscape. And as we stated previously, if we're using these filter-wise normalized directions, these generally flatter loss landscapes is more correlated with lower generalization error. So this is probably a good thing for us if we see a loss landscape like this. Sorry, was there a question? Sorry. Okay. So this next example, here we're looking at the effect of increasing the number of layers in the neural network. So as we go from left to right, we're adding layers to the neural network, and the difference between the top and the bottom is that the top uses skip connections, whereas the bottom does not. So we see that as we increase the number of layers in the neural network, we have more spontaneous transitions from convex to chaotic regions in the loss landscape. And we also see that the addition of the skip connections generally keeps the loss landscape better behaved than without them. And so here, what the authors highlight is that this shows the importance of using good initializations for the optimizer because we have all of these regions of non-convexity. And then some other notes that the paper makes is that originally this loss landscape is in a very, very high dimension. But because we're projecting into these just 2 dimensions. Non-convexity in these visualizations does correspond with non-convexity in the full dimension, but convexity in these visualizations does not necessarily equate to convexity in the full dimension. So even if we see like a pretty convex, well-behaved looking loss landscape in these 2 directions, it's not necessarily true that that's the case for the full problem. Okay. So here are just some summarizing remarks and some potential like future work that could be done along these lines is that the authors of the main paper disregard generalization errors as we discussed previously. So one logical question would be, would the improvements in the approximation or optimization errors resulting from using this regulating data outweigh any potential associated increases in generalization error? Another thing is that we only are looking at 2 particular projection directions. So it would be interesting to see how these loss landscape visualizations change when different directions are picked. And then finally, the main paper does mention that the pin loss and of their regulatory pin loss is a multi-objective loss function. So an interesting question would be to see how weighting those objectives non-uniformly would affect the addition of regulating data on the loss landscape. Okay. Do we have any questions?
Thank you, Paula. That was an excellent talk.
Thank you.
Do we have questions for Paula?
Paula, I'm Amir from Brown.
Yes.
I have one question. Can you go back to the pecan versus pin loss? Yeah, here. Go ahead. Go ahead. One more. Yeah, this one. So if you see this loss function, basically the pecan loss in terms of magnitude, the lowest magnitude is 1.54, right? For pecan, whereas for pin, it is 1.21. So if you see the blue regions of the loss landscape, pin loss landscapes, so they are much better locations. And because actually they are the locations even better than pecan, right? In terms of, if they are comparing this fairly, then they should keep everything fixed. Optimizer, initialization, number of parameters, number of location and the number of data points, right? So why pin is not working in this case? Because it has much better,
Yeah, I think it's a little bit hard to see in this figure, but it's very bumpy everywhere. And it's a little bit hard to see with this
in
color.
terms of magnitude, if you see pecan, the minima magnitude is 1.54, whereas pin minima has 1.21 magnitude. And there are several minimas if you see the blue region. So I'm not sure why pin is not behaving well in this case.
Yeah, I think it may be that their initialization of the optimizer might not have been very great, because here for pin, I think it's a little bit hard to see, but it's pretty non-convex around the minima there. Whereas here it's less non-convex around it.
So I think so Amir's point is that, so there are a large location of the loss function, they are pretty small loss. So if we go to anywhere around this location, we are good.
Yes.
I think that's the Amir's point. Although it's oscillated, right? It's also bumps, but they are all good. They are all good solutions. That's definitely an interesting part.
Yeah. I mean that's the comment I wanted to make on Lulu's statement, because he, as Lulu said, the loss function without data was basically much better compared to with sparse data, the previous case. But in terms of magnitude, the local minima magnitude with data, it was much lesser. I think it's of the order of -12 something compared to the plus values for without data. So I think it can make a big difference in terms of magnitude.
Yeah.
Yeah, thank you, Paula.
No, thank you.
I think this goes back to my MSCO again, that the choice of mu is very delicate, of course, in these methods, in penalty methods. So depending on what you choose, if they had done a study keeping all the parameters the same and just varying mu, they'll find even pecan will have a very difficult loss landscape in general. And in fact, it could be fluctuating. The minima could be widely different.
Yeah.
So yeah, my question earlier was actually in terms of imposing the boundary conditions in a hard way is exact, not approximate. So that was probably, we can talk about it later. Yeah, it's a discussion.
Suku, for that, there's also a group at, I was just at Lehigh University a couple of weeks ago, and there's a group, Frank Curtis, who's a big optimization guy, yeah. So he and my former student, Xu Yang, are trying to also do something similar, not even go to the Lagrange multiplier, to the augmented Lagrangian multiplier, but have a hard constraint, impose this with, reformulate pins with hard constraints, not just the boundary conditions.
Right.
Totally reformulate pins.
Right.
And see. Then it could become extremely expensive, but nevertheless.
You mean including the PDEs itself as hard constraints?
Yeah, including the PDE,
But that might make it very rigid. It might make the method
that's why. Yeah, they just want to see actually what is the landscape that they optimize the loss function, which is that's why I thought I suggested to Paula to put all three things together. As you know, this work number 3 was presented in the course last Wednesday. We presented the paper by Lee. How
right. I saw that landscape. I remember.
Yeah, and also, Paula, if you unravel if you unravel the ResNet, you see that that's basically an ensemble of many kind of different pathways to connect the input and the output, and that ensemble creates some smoothness. But again, one cannot draw conclusions as how much convexity you induce. It would be nice to quantify that by sampling different dimensions,
right?
Instead of 1 and 2 and so on. But with I think Lulu, TSNE does that, right? TSNE, does it take TSNE just take the 2 principal, or it takes different ways to visualize different principal directions?
So in this paper, they have a special way to do this. Not the TSNE, they use another way.
Okay, yeah, different method, yeah.
Is it possible to sample the worst direction somehow, a priori?
Yeah, that's a good point.
I guess I'm not really sure how you would measure the worst directions, but yeah.
In terms of eigenvalues or something, and just look at descending eigenvalues or the most important ones. I don't know how to call it.
Yeah, lots to be done. Lots to be done. Very informative. I thought it was very informative, Paula. That's excellent.
Thanks a lot. Yeah.
Thank you.
I think we have 2 comments from Professor Erhard. If he's still
here. Yeah.
I think he left probably.
All right. So I think this was related to this. One of them was correcting the Navier-Stokes problem, and then the labeling of the figures is just because I copy pasted from different figures so that they're easier to compare. So just ignore the labelings of B and C. But yeah.
Do we have more questions for Paula? If not, thank you, Paula, for this presentation.
Thank you.
And that brings us to the end of today's seminar. Thank you all for tuning in, and have a great weekend ahead. Bye.